Hello all. As I was about to start recording this video, there was an incident I didn't expect, which was an earthquake. Okay, so since yesterday there have been lots of earthquakes where I live. But okay, I'm good. Nothing happened. So let's start with the video. This is a walkthrough of a past paper from January of 2024. Okay, and we will work on Unit 5. Okay, so I have the solutions, my solutions next to me, and I also will open. Let me see. Okay, let's also open the mark scheme. I had it somewhere. Don't know. So it's this one. And on top of earthquakes, we also have a storm. So yeah, that's great. Okay, so let's go back to the paper. Thank you for all of you who are leaving comments in my videos. Thanks for following and subscribing to my channel. I'm trying to, develop it and upload more material and so on. So it's kind of encouraging to see people engaging with what I upload. And I'm hoping that this channel will grow even more. And as I said multiple times, I'm gonna gradually include other types of materials as well. So let's go. This is Unit 5 again. Section A. These are 1 mark questions. There are always 10 1 mark questions. So let's go. Question 1. Ice at 0 degrees Celsius melts into water at 0 degrees Celsius. Which row of the table gives the changes in mean molecular kinetic energy and mean molecular potential energy as the ice melts? Okay, so in phase changes, remember that the temperature remains the same. So let's write it somewhere. So in phase changes, and when I say phase changes, I mean from water to steam, from water to ice, and so on. So in phase changes, T is a constant, okay? So, the kinetic energy doesn't change, okay? So we are left with options A and B, all right? So why do we know that the kinetic energy doesn't change? Because the kinetic energy is proportional to 3/2 kT. So if T is constant, so is the kinetic energy. But the potential energy increases, okay, because the bonds that hold the ice together, okay, break. So we increase the potential energy, okay? I think in one of my lessons, this was a point of confusion in that, for example, if the ice has a molecular potential energy of -30, okay, in some arbitrary units, maybe -30 joules, then the water will have -5 joules, which means that the potential energy actually increases because -5 is larger than -30. I hope this makes sense. So the answer is B. Right. Question 2. Astronomers can use stellar parallax to determine the distances to stars. Which of the following statements is correct? Measurements are made against more distant stars, which is actually the answer, okay? I mean, there is no reason to go over the the other options, but let's go quickly. So B says that, excuse me, B says that stellar parallax can only be used for distant stars. That's wrong, okay? The luminosity of the star must be constant. No, that's refers to standard candles and stuff like that. D, the parallax effect is greatest for the most distant stars, which is totally wrong. So let's move on. Question 3. The mass of a muon is 0.113 U. atomic mass units. Okay, which of the following is equal to the equivalent mass energy in joules of the muon? So delta E is delta M C squared. Okay, so you can immediately eliminate option B, as you can see, right? Because we are dividing with C squared. All right, so let's see. Actually, I have to make sure. Let me read the units they give you. So the constants are over here, okay? So, okay, they give you the atomic mass unit in kilograms. So you see that it's 1.66 times 10 to the minus 27. So if we go back, where was it? Here. So we have 0.113 times 1.66 times 10 to the minus 27, like you just saw, times 3 times 10 to the 8 squared, and the answer is no, it's not A. Sorry, it's let me see, C. Okay, excuse me for the mistake. So 4. A mass is oscillating with simple harmonic motion. Which of the following statements about the acceleration of the mass is correct? Okay, option A, the acceleration is always in the opposite direction to the velocity. That's not correct, because sometimes they are in the same direction, okay? Because, for example, if you have a pendulum and it's in this position moving back, okay, the acceleration is in the same direction, right? So that's wrong. B, the acceleration is always in the same direction as the velocity. That's also wrong. The acceleration is always away from the equilibrium position. That's wrong. The acceleration is always towards the equilibrium position, which is the correct answer, right? Because if you are here, the acceleration wants to take it back to the equilibrium. If you are over here, I'm using the pendulum, but it works with springs as well. The acceleration wants to go back to the equilibrium position, and so on. And when you're in the middle, you have no acceleration, okay? Because remember that acceleration is minus omega squared x. So at x equal to 0, acceleration is 0. All right. It's funny that we are talking about oscillations while earthquakes are going on here where I live. So that's a form of oscillation. So it's a little bit crazy. So 5. Which of the following correctly describes the spontaneous nature of radioactive decay? So radioactive decay is a natural process. Okay, that doesn't mean that, doesn't explain the spontaneity, okay? B, radioactive decay is a random process. Okay. I don't even understand what they mean by random, so that's wrong. C, we cannot influence when the decay will occur, which is the correct answer, okay? And then D, we cannot predict when the decay will occur. That's not correct, okay? So C is the right answer. Is it though? I'm a little bit doubtful for some reason. Let me see. Where was the it was open somewhere. Okay. Okay. That's okay. Let me close this. Oops. Here and here and here. Okay. So this is the mark scheme. For 5, they say C is the only correct answer, like we do it, and then they say that A is not correct because that this does not make the process spontaneous. Okay, they provide the same answer, so no more insights. So let's move on. Okay, question 6. The planet Mercury orbits the Sun in an elliptical orbit. As a result, the speed of Mercury varies as it orbits the Sun. Which row of the table shows how the speed and gravitational potential energy of Mercury change as Mercury approaches the Sun? Approaches means gets closer, okay? So here we need to use the fact that the gravitational potential energy is minus g m over r, okay? So if r becomes smaller, this means that u will become more negative, okay? Which means that it actually decreases, okay? But because the gravitational potential energy decreases and the total energy is conserved, it means that the kinetic energy will increase, which means that the speed will increase. So the answer is actually B, okay? It's a little bit of a counterintuitive problem, but you can think about it like imagine Mercury kind of falling onto the sun. So as it falls, just like an object falling, I don't know, from the sky down to Earth, the velocity will, the speed will increase, right? So it's the same case pretty much. So the answer is B. Right. Question 7. A mass oscillates with simple harmonic motion. The mass has an angular velocity of 2 radians per second and a maximum velocity of 10 centimeters per second. Which of the following gives the magnitude of the amplitude A of the oscillation in centimeters? So the maximum velocity is equal to omega times A. How do I know that? I think okay. If they don't have the formulas, I'm going to explain it otherwise. Let me see. Unit 4. Okay, good. Do they provide? Sorry, that's unit 4. We need unit 5. I'm sorry. Yes, they do. Okay. So this is the velocity, right? The maximum velocity occurs when, okay, the velocity depends on a sign, okay? But sine omega t, what's the largest value? The largest possible value of sine omega t? 1 or minus 1, right? So the maximum velocity is then omega a times 1. So omega a, okay? So let's go back. Okay, I'm trying to prove what I say. Okay. Okay, since we found that, we have to solve for a, which is v max over omega, v max, okay, 10 over 2 pretty much, right? So B is the right answer, yeah. 10 over 2 in centimeters, okay, so we are fine. Right, question 8. A mixture of helium gas and hydrogen gas is kept at room temperature. Which of the following is correct? All right. The mean kinetic energy of the helium molecules is greater than the mean kinetic energy of the hydrogen molecules. Can we even reply to that? We cannot, because we need to know. Wait, the mean kinetic energy of the molecules, not the whole gas. I'm sorry, I confused you. Anyway, I'm pretty much thinking of this formula. The mean kinetic energy, this one, is given by 3/2 kT, right? So since the temperature is the same for both molecules, then A is wrong. Okay. B, the mean kinetic energy of the helium molecules is less than the mean kinetic energy of the hydrogen molecules. This is also wrong because it's the same actually when we talk about the kinetic energy. The mean square velocity of the helium molecules is greater than the mean square velocity of the hydrogen molecules. Okay, so let's solve for the velocity. So V squared is 3 kT over m, okay? So the heavier molecule, which is helium, will have a lower velocity. So the mean square velocity of the helium molecules is less than the mean square velocity of the hydrogen molecules. So D is actually the correct answer, okay? So if you're talking about the kinetic energy of two different species of molecules, if the temperature of these molecules is the same, they have the same kinetic energy actually, but the velocity does depend on mass, as we show here, okay? So the heavier the molecule, the lower the velocity for the same temperature, all right? Now, question 9. The graphs show how the radiation intensity varies with wavelength for star X and star Y. The surface temperature of star X is Tx and the surface temperature of star Y is Ty. Which of the following statements is correct? Ty larger than Tx because the peak intensity for star Y is at the lower frequency. Okay, first of all, Tx is larger than Ty, okay? So we know that because this is how the curves go. I mean, the black body radiation curves, okay? So Tx is larger than Ty, which means that it's either this or that, okay? It's either C or D, okay? So I'm trying to say that this and that are wrong. So C says that Tx is larger than Ty because the peak intensity for star X is at the lower frequency, which is not correct because smaller wavelength means higher frequency, right? So it's D. Remember that C is lambda F, so F is C over lambda, right? So if lambda is smaller, then the frequency is larger. So D. Now, question 10. The Earth has 10 times the mass of Mars and twice the radius of Mars. The gravitational field strength at the surface of the Earth is Ge. The gravitational field strength at the surface of Mars is Gm. Which of the following gives the relationship between Ge and Gm? Okay, so how, let me see how to do this. So Ge for the Earth is G times the mass of the Earth over R squared. G of Mars is G, and then they say 10 times the mass of Mars, so times the mass of the Earth over 10 for the mass of Mars, and then the Mars has half the radius pretty much, which means that we have R over 2 squared, which gives us Gm4 over 10 and then R squared, okay? So this part over here is G for Earth, right? And 4 over 10 is simply 0.4, right? So the answer is, wait, so this is 0.4 GE, but we have to solve for GE, so GE is 10 over 4 G Mars, which is 5 over 2, which is 2.5 G Mars, so the answer is A. Okay, I don't know why I'm having difficulties. Maybe it's the earthquakes and the storms and so on. Maybe it's a primal thing, but anyway, so it feels a little bit harder for some reason. So, or maybe it's because I haven't done Unit 5 in a while. So anyway, Section B, Question 11. The Hertzsprung-Russell diagram below shows some groups of stars. P, Q, R, and S refer to the different areas on the diagram. Okay. Describe a possible evolutionary path for stars originally in area P. So that's the area P, okay? So that area is the blue giants, okay? P is blue giants. So stars with really, really high luminosity and high surface temperature, okay? Because remember that the temperature increases to the left, which they show you actually over there, okay? So, so the blue giants are massive main sequence stars. Okay, so when they grow old, they become red giants. Okay, they become larger, so their luminosity might even increase a little bit, but the temperature drops significantly because of if you have the surface of a star actually increasing, the temperature decreases, right? Because you have lots of loss of heat, pretty much. Imagine a gas expanding, something like that. So we go to S, right? And then once the red giant phase ends, we go to Q. So that star will become a white dwarf. Okay, so S are red giants and Q is white dwarfs. So possible sequence will be P, S, Q. All right, let me see what the mark scheme says. I'm curious. So stars in area P are massive main sequence stars. Okay, we said that. Stars in area P evolve into area S, and stars in area S evolve into area Q. Stars in area S are red giants, and stars in area Q are white dwarfs. So we are correct, pretty much. Moving on. Question 12. This is a 4-mark question, so it should take you 4 minutes. Remember the rules I told you to remember. So a simple pendulum has a period of 2 seconds on Earth. Calculate what the period would be if the pendulum was on the planet Venus, and they give you the mass of Venus and the radius of Venus. Okay, so it's a little bit of an involved problem, but let's think about it. Okay, they do give you the radius of Venus. So the period is 2 pi, the square root of L over G on Earth, and this is 2 seconds. Okay, G for Venus is equal to G, the gravitational constant, times the mass of Venus over R of Venus squared. Okay, so if we plug this the constants in, we have 6.67 times 10 to the minus 11. We're given the mass of Venus in kilograms, so that's cool. And then we have to divide with the radius in meters, and it is given to us in meters, so that's good. By the way, just for the trivia of this situation, the planet Venus is considered the evil twin of Earth because they have about the same size and mass and so on. But the surface of Venus is like hell. Okay, it's really hot because there is a huge atmosphere, lots of gases, which creates a really, I think the pressure on the surface of Venus is 100 times more than the pressure on the surface of Earth. So it's hell. Anyway, if we plug everything in, we get 8.87 meters per second square. So you see that G on Venus is very similar to G on Earth. Okay, so the period on Earth over the period on Venus, we can divide this, will be 2 pi square root of L over GE, and I'm doing this because I don't know we don't know the length of the pendulum, so we want to get rid of that. So L over G Venus, okay, 2 pi goes away, L goes away, so the periods are related by the square root of GV over GE. So the period on Venus would be the square root of GE over G on Venus times the period on Earth, which ends up giving us 2.1 seconds. Okay, so compare these two. I mean, they are really close. Why is that? Because G is very close. Okay, so because the G's are very similar. All right. Okay, moving on to question 13. A particular line in the spectrum of light from a source in the laboratory has a frequency of 6.173 times 10 to the 14 hertz. The same line in the spectrum of light from a distant galaxy has a frequency of 6.142 times 10 to the 14 hertz. Deduce what can be concluded about the distant galaxy. You should include a calculation. Okay, so first of all, we see that the frequency of light as we receive it from the distant galaxy reduces, okay, which means that the wavelength increases, right, because c is lambda f, right? So if f decreases, lambda increases. Larger wavelength means something that is redshifted, right? So the galaxy is moving away from us, all right? So we can actually calculate its speed, okay? They don't mention it explicitly, so we can use the Doppler shift, which is given by the difference in frequencies measured in the lab and the one from the distant galaxy over the frequency in the lab is equal to the velocity of this galaxy over c, right? So v is c times this difference over the frequency in the lab. Okay, what's the difference? We have, let me think, 6.142 minus, which is the velocity, sorry, the frequency of the light from the distant galaxy minus the one in the lab, which is 6.173, and we have to multiply with 10 to the 14, and we also have to multiply with c, don't forget that, 3 times 10 to the 8, right? Divided by the frequency in the lab, which is just 6.173 times 10 to the 14. 10 to the 14 and 10 to the 14 go away. And if we do the calculation, we find minus 1.51 times 10 to the 6 meters per second. Okay, and also you have to specify that the galaxy is moving away from us. Okay, so this is a redshifted galaxy. Okay, now question 14. A tire on a racing bicycle. So a tire on a racing bicycle contains nitrogen at a temperature of 22 degrees Celsius. The nitrogen in the tire has a volume of 2.85 times 10 to the negative 4 cubic meters. The pressure of the nitrogen in the tire is 5.75 times 10 to the 5 pascals. Nitrogen is pumped into the tire. The volume of the tire remains constant. Okay, that's key over there. This one, the constant volume. The total mass of nitrogen in the tire, including the added nitrogen, is 2 grams. Okay, for the total. Calculate the increase in pressure of the nitrogen in the tire. Assume that the temperature remains constant. Okay, and they give us the mass of a nitrogen molecule. So, first of all, let's find the number of molecules, okay? So, the mass is 2 grams, right? But the mass is given by the number of nitrogen molecules times the mass of one nitrogen molecule, right? And this is equal to 2 grams, which is 2 times 10 to the negative 3 kilograms, okay? Don't forget to convert to kilograms because they give us the mass in kilograms, okay? So N is 2 times 10 to the negative 3 over 4.67 times 10 to the negative 26. So we are off to a good start by finding the number of nitrogen molecules, which is 4.28 times 10 to the 22, close to Avogadro's number, okay? Now the final pressure, which we need to find, is PF times the volume. This is equal to NKT, okay? This is why we needed the N. So we can solve for P final to find NKT over V. This is 611.36 kilopascals. Okay, I went a little bit fast. For n, we use that. The Boltzmann constant is 1.38 times 10 to the negative 23, I think, right? Let me check. Yes, 1.38 times 10 to the negative 23. My memory is still working. Okay, that's good. Good news. So let's go back. Temperature is the final temperature, and the final temperature is also, the temperature is constant, so the final initial temperatures are the same, and it's 22 degrees Celsius. Don't forget to use 293 Kelvin, okay? So this is what I use for temperature there, and for volume, we use the volume that is given to us, and we find the final pressure. Okay, so all you have to do is to find the difference in pressure, which is pretty much we have to subtract 611.36 times 10 to the 3 pascals minus 5.75 times 10 to the 5 pascals gives us 3.64 times 10 to the 4 pascals. Okay, so this is the answer. Okay, so this is how you have to work it out. So moving on to question 15. A teacher used liquid nitrogen to demonstrate low temperature physics. The teacher dropped a peeled banana at room temperature into a flask of liquid nitrogen. Explain why the liquid nitrogen boiled when the banana was submerged in the liquid nitrogen. Okay, so the banana is at room temperature, so T room. So it transfers energy to the liquid nitrogen, okay, providing the latent heat of vaporization to the nitrogen liquid. Okay, so there is nothing else to say. I mean, liquid nitrogen is at the much lower temperature than the temperature of the banana, so the nitrogen liquid boils pretty much. Okay, B. Let me see. During the demonstration, the liquid nitrogen remained at its boiling point in a large flask. The teacher estimated that at least 0.5 kilograms of liquid nitrogen was needed to cool the banana from room temperature to the temperature of the liquid nitrogen. Assess the accuracy of the teacher's estimate. So they give us the latent heat of vaporization of nitrogen, boiling point of liquid nitrogen, specific heat capacity of banana, mass of the banana, and room temperature. Okay, so let's see how much energy we need to drop the temperature of the banana. So delta E is C times M times delta theta, right? So C for the banana is this one, 1.76 times 10 to the 3. And then the mass of the banana is 0.118. So we are calculating how much energy we need to drop, how much energy the banana will give to the liquid nitrogen pretty much, okay? So 0.118, and then the temperature goes from 292 to 77.4. So we need 44, we will give 44.57 kilojoules to nitrogen. Okay, so for nitrogen, when nitrogen boils, we need energy given by delta E is delta M times L, right? So we need to calculate how much nitrogen will boil pretty much, right? So delta M, let me think. So delta M is delta E over L, and delta E is what we just calculated. So 44.57 times 10 to the third over the latent heat, which is 1.98 times 10 to the 5. So 0.23 kilograms is enough. Okay, so the teacher's estimate is grossly wrong. So the teacher's estimate is wrong. Okay. All right. This was question 15. Let's move on to question 16. Pluto is a dwarf planet. For some of us, it's still a planet in our hearts, but okay. Dwarf planets are planets that do not have their own clear orbital path. This is the definition, okay? Meaning that the orbit of the planet does not cross the orbit of some other object, okay? So anyway, Pluto is a dwarf planet in the outer regions of our solar system. Pluto moves in an approximately circular path around the Sun. The mean radius of the orbit is 5.91 times 10 to the 12 meters. Calculate the intensity of radiation from the Sun incident on Pluto. They give us the radius of the Sun and the surface temperature of the Sun and the distance. So, first of all, let's find the luminosity on the surface of the Sun. So we need the Stefan-Boltzmann relationship, which I remember, but let's double check. Okay, maybe here. No. Strange. Here. This is what we need. And sigma is given over here. Where is it? Here. All right, so let's go back to the problem. So L of the Sun is sigma A T to the fourth, so 5.67 times 10 to the negative 8. The surface area of the Sun is 4 pi times its radius squared, which is 6.96 times 10 to the 8 squared, and then temperature to the fourth. Okay, so 3.91 times 10 to the 26 watts. That's a lot of energy. How much intensity makes it to the surface of Pluto? Let's see. We need to use the radiation law. So L surface over 4 pi r squared, where r is the distance, the radius of the orbit of Pluto. So if this is the Sun and Pluto is over here, we need to use this radius. Okay, so if we plug in numbers, we have 3.91 times 10 to the 26, which we just calculated over 4 pi, and then r squared, which is 5.91 times 10 to the 12 squared, so 0.89 watts per square meter, which is much less than an LED lamp, I think. So anyway, this is the intensity of radiation from Sun incident on Pluto. B, calculate the time in years that Pluto takes to make one complete orbit of the Sun. And they give us how much 1 year is in seconds and the mass of the Sun. Okay, how are we gonna think about this? So we need to think in terms of the centripetal force exerted on Pluto from the Sun, which is gm m over r squared, which is the gravitational law, like the gravitational force plays the role of the centripetal force, and this should be equal to m omega squared times r, where m is the mass of Pluto, okay? And capital M is the mass of the Sun. So the mass of Pluto cancels. So omega squared is g times the mass of the Sun over the radius cubed, okay? And since we are looking for the period, recall that omega is 2 pi over the period, so omega squared is 4 pi squared over the period squared, and this is gm over r cubed. And if we solve for t squared, we find 4 pi squared r cubed over gm, okay? And then we have to take the square root of that. Square root of 4 pi squared times r cubed over gm. I don't think I ever mentioned this before, but usually when you derive formulas, it's good to not use numbers until you reach a final expression. This is the final expression, okay? So what I'm saying is that it is tempting to start plugging in numbers in there, but usually it's gonna confuse you. I don't know if it works for you, fine, but in general, I recommend you reach a final formula, and then once you reach that final formula, you plug in numbers. And if we do plug in numbers, we find 7.89 times 10 to the 9 seconds, which is 249 years, guys. Okay? So if you lived on Pluto, you will have birthdays every 249 years, okay? So let's move on. Question 17. Skylab. Okay, let me fix my notes here. Okay. Skylab was an early space station that orbited the Sun. Skylab contained a body mass measurement device. This device was a chair connected to a stiff spring. Now I'm curious, what is Skylab? I never heard of it before. So let me see. Okay, Paper Lords is where I get your papers from. So Skylab. Okay. America's first experimental station, Skylab, was designed for long durations. Okay, let's go to Wikipedia. Well, okay, it was the United States' first space station launched by NASA, occupied for about 24 weeks between May 1973 and February 1974. So it was before my birthdays, okay. Even though I'm 1,000 years old, I'm not that old. Okay, so it was operated by three trios of astronaut crews, Skylab 2, 3, and 4. Okay, interesting. Okay, I guess this was the precursor to the International Space Station or something. So anyway, let's go back to the paper. Right. Astronauts, okay, this is A. Astronauts in orbit about the Earth are sometimes described as weightless, although they do experience a weight force. Explain why astronauts may be described as weightless. Okay, so let's answer this. The weight of the astronaut provides the centripetal force that keeps him on orbit, or her, that keeps him or her in orbit. Okay, but there are no contact forces. Okay, so what we experience as weight is actually the contact force from wherever we are. Okay, so there are no contact forces. So there are no contact forces. So to visualize it, I'm going to erase it later. So this is the Earth, and you are here in the space station, okay? And you are not, this is orbiting, and you are orbiting, okay? So your weight plays the role of that force I mentioned, okay? So you don't experience force because you move along with the spaceship pretty much, okay? So your weight is there, but there is no contact force with a floor like we experience here on Earth, for example. So you don't feel your weight. Okay, what does the mark scheme say? I'm feeling a little bit insecure today. Let's go to 17. Okay, the astronauts must experience centripetal forces they orbit the Earth, okay? Or the weight of the astronaut acts as a centripetal force, which is what we answered. They do not experience normal contact forces. Okay, so we were right. Let's move on to part B. The spring was tested without oscillating. A force of 175 newtons was applied to the spring, and the spring deformed by 28.9 centimeters. When no one was sitting in the chair oscillated with a period of 0.858 seconds. When one of the astronauts sat in the chair oscillated with a period of 2.26 seconds. Calculate the mass of the astronaut. Okay, this is a little bit involved. Let's start with the first piece of information. So when a force of 175 newtons was applied to the spring deformed by 28.9 centimeters, which means that Kx is equal to that force that was applied, right? So K, we can use this to calculate K, the spring constant, okay? So K is F over X. So 175 newtons over, we need to convert that to meters, 0.289, which gives us 605.53 newtons per meter. Okay, when no one was sitting in the chair oscillated with a period of 0.858 newtons. Okay, so since this is a spring, we can just use T equal to 2 pi square root of mc of the chair, the mass of the chair, over K. So T squared is 4 pi squared mc over K. So we can use this to calculate the mass of the chair, okay? So the mass of the chair is kt squared over, let's call this Tc, which is the period of oscillation for the chair, okay? So ktc squared over 4 pi squared, which gives us 11.29 kilograms. Okay, then the last piece of information, and I will need a clean page, okay, is that when one of the astronauts sat in the chair oscillated with a period of 2.26 seconds. So let's call this T of chair plus astronaut, okay? And this is 2 pi times the square root of m of chair plus m of astronaut over k, okay? So m chair, and I'm using wait, what am I saying? So m chair plus m, oops, okay. So m chair plus the mass of the astronaut is equal to ktc plus a squared over 4 pi squared, and this is 78.34 kilograms. So we have to subtract the mass of the chair from the mass of the astronaut there. So mass of the astronaut is 67.05 kilograms. Okay, I hope this makes sense. Okay, is there anything else to say here? I think not. So let's move to question 18. Question 18. Kruger 60 is a binary star system quite close to the Sun. The wavelength, the lambda max, at which the intensity of radiation is a maximum, is 850 nanometers for Kruger A and 1700 nanometers for Kruger B. A website states that the surface temperature of Kruger A is double the surface temperature of Kruger B. Assess whether the website statement is accurate. Okay, so we have to think of Wien's law here, because Wien's law tells us that the maximum wavelength times the temperature, the surface temperature of a star, is 2.898 times 10 to the negative 3 meters Kelvin. So we can solve for temperature pretty much, right? T is 2.898 times 10 to the negative 3 over lambda, okay? So for the first star, the temperature will be 3409.4 Kelvin, okay? So you just plug in this lambda and this lambda pretty much, okay? And then T2 is 1932 kelvins, all right? And if we divide them, we find 3409.4 over 1932 gives us 1.76, which is not accurate, okay? I mean, it says double the surface temperature. It's not double, it's just 1.76, so wrong, okay? Right, B. Kruger B can be used as a standard candle. Describe how standard candles can be used to determine the distance to galaxies. So, first of all, okay, it's 4 marks, so give or take, you have to have like 4 arguments when you address this kind of question. So, standard candles, the first thing we're going to say is that standard candles are stellar objects okay, of known luminosity. Okay, once you find, you have to find a standard candle, okay, so find a standard candle. And then once you find a standard candle, since you know the luminosity of that object, okay, you can measure the intensity of radiation received from that celestial object here on Earth. So measure the intensity of radiation on Earth, okay? And then once you know that intensity, calculate the distance, okay? So calculate D by using the radiation law, which tells you that I is 4 pi D squared, so D squared is L over 4 pi I, and you can find the distance, okay? So the magic here is that you know the luminosity of this object. So once you know the luminosity, all you have to do is to measure the intensity of radiation on Earth and then calculate the distance. So part C. NGC 1357 is a spiral galaxy moving away from the Milky Way at a speed of 202 times 10 to the 6 meters per second. The spiral galaxy is 8.7 times 10 to the 23 meters from the Earth. Calculate a value for the age of the universe in years. Okay, so how do we think about this? Okay, so we're given the velocity and the distance. Okay, so remember that the velocity of a galaxy is given by h naught times d, where h naught is the Hubble constant. Okay, so we have the velocity and the distance here, so we just plug in and see what we get. So h naught is v over d, and this gives us 2.32 times 10 to the minus 18 seconds to the minus 1. Okay, and then if you know h naught, okay, here we are just using one data point pretty much. Remember that Hubble made that plot of velocities and distances, etc., and he found the slope of the curve, and that's how he calculated h naught. Okay, in our case we just use one data point, but okay. Once you know the Hubble constant, the age of the universe can be calculated as the inverse of that constant. Okay, so 4.31 times 10 to the 17 seconds, which in years they give us that. We have to divide by that to find. If we divide by 3.15 times 10 to the 7 seconds per year will give us 1.37 times 10 to the 10 years, okay? Which is not accurate, okay? I mean, I told you in the beginning that this is not proper science. In proper science, you need many such values, many such pairs of values, so you can plot it, calculate the gradient. The gradient is going to be your h naught, and then you can find the age of the universe. Let's move on. So, question 19 is, again, from what I studied in my life, which was nuclear physics. So, the graph shows how the binding energy per nucleon varies with the number of nucleons. Okay. Explain why energy is released when a nucleus undergoes fission. Okay, fission is when you have a heavy nucleus, such as the one they give us here, for example, and it splits into two lighter nuclei, okay? So, for example, it can split into this and, I don't know, something else, okay? So you see that the daughter nuclei, as they are called, have a higher binding energy per nucleon than the parent nucleus. Therefore, energy is released in this process, okay? Let's erase this because we might need it later. Let me go back to the black marker and let's answer this. A larger nucleus, okay? A larger nucleus with a lower binding energy splits into two nuclei and neutrons are also emitted. Actually can also emit, this is the proper way to put it, okay? So in fission, you don't only split the nucleus into two, you also release some neutrons usually, okay? So splits into two nuclei which have a larger binding energy, okay? Thus energy is released. And that's the answer. Okay, a nucleus of uranium-238 undergoes fission. One of the fission products is SN. I should remember this. What's SN? It's tin or no? Let me see. SN element. I should know this thing. Tin, yeah, okay. Good, I remember. Okay, so estimate the energy in MeVs released in the fission. You should use values from the graph. Okay, so the binding energy per nucleon for uranium-238 is this one. So it's, okay, this is 7. Okay, this is 7, 7.12. Okay, so about 7.5, let's say, is the binding energy per nucleon for uranium-238. So B over A before is 7.5 MeVs, and the B over A after the fission is about, it's this one over here, so about 8.5, okay? 8.5 MeVs. So the difference between these two values is about 1 MeV. Okay, thus we will have about 238 times 1 MeVs of energy available. This is what they asked to find. They asked us to find, right? Estimate the energy in MeV released in the fission. Okay, so I don't know why I put that 0.1, just to put 238 MeVs. So pretty much I'm finding the binding energy per nucleon difference. So another way to think about it is that between this nucleus and this nucleus, that's about 1 MeV of difference. So since uranium-238 has 238 protons and neutrons, we will get 238 MeVs, because this is the essence of what binding energy per nucleon means. Okay, so 238 MeVs is what we will get from this fission. Okay, this is a crude calculation. Actually, let's see what the mark scheme says. Okay, this is question 18 or 19? 19. Okay, they find 240. Okay, that's good enough. It works for me. So let's move on. C. One fission product is strontium-90. Complete the nuclear equation for the decay of strontium-90. Actually, it's the Vita decay. I mean, I don't know why they didn't say that. So, okay, we have 38. The Vita particle has a charge of -1 and a mass number of 0, okay? And the neutrino has 0 mass and 0 charge, okay? So the nucleus Y has to have 90 protons and neutrons. The mass number has to be 90 because we have 90 before, therefore we have to have 90 after, okay? And to get 38, we need 39 for this nucleus, okay? 39 minus 1 gives you 38. So the left-hand side and the right-hand side match. So that's it. Okay, part 2. In Georgia, in December 2001, some men discovered 2 small canisters in a forest. The canisters were hot and had melted surrounding snow. The canisters were later identified as containing strontium-90. The activity due to the strontium-90 in one canister was measured as 1.29 times 10 to the 15 becquerels. Calculate the rate of energy release in watts due to the strontium-90 in this canister. And they give us the energy released in each decay. So how do we think about this? It's actually straightforward. Okay. What does activity means? It means decays per second. So we have this much energy released per second, okay? And we are given the activity, so we have to just multiply the two. So 129.5 times 10 to the 15 seconds to the -1 times 0.546 times 10 to the 6, since this is MeVs, times 1.6 times 10 to the -19, because, okay, we have to convert MeVs to EVs by multiplying with 10 to the 6, and then we have to convert EVs to joules because we are asked to find this quantity in watts. So the answer is 113.13 watts, okay? All right, part 3. The authorities claim that the canisters were 50 years old. The activity of each canister when new was 3.7 times 10 to the 15 becquerels. Assess the accuracy of the claim, and they give us the half-life of strontium. Okay, recall that if we have the half-life, we can find the decay constant using ln of 2 over t 1/2, the half-life. So in years, this is 0.024 years to the -1. Okay, this is an unusual kind of unit to use, I know, but okay, let's work with it. The activity behaves the same way as the decay law. So A is A naught e to the minus lambda t. Okay, so okay, the activity now is 1.29 times 29.5 times 10 to the 15 because it's given to us there. This must be equal to 3.7 times 10 to the 15 times e to the minus lambda t, okay? This and that cancel. So lambda t is pretty much the ln of 3.7 over 1.295, and t, if you work this out, it works to 43.7 years, which is not accurate, okay? This is a straightforward application of the radiation law. Okay. 20. The penetration of nuclear radiation through materials depends upon the ionizing power of the radiation. A teacher tested an unknown radioactive source. He set up the source in a Geiger-Müller tube as shown. The initial count rate is determined without an absorber between the Geiger-Müller tube and the source. When an aluminum sheet of thickness 0.5 centimeters was placed between the source and the GM tube, the count rate decreased to background level. The teacher then removed the aluminum sheet and replaced it with a sheet of paper. There was no change in the initial count rate. Explain which type of radiation is emitted from the source. You should refer to the penetration of each type of radiation through each sheet of absorber. Okay, so let's answer this. The radiation, okay, cannot pass through aluminum. Okay, so it should be alpha or beta, since gamma passes through aluminum. But the sheet of paper will stop alpha particles, okay? Would stop alpha particles. Therefore, we are dealing with beta particles, which is the answer. Okay? The count rate R recorded after gamma radiation has passed through a thickness X of lead is given by R equals to R naught e to the minus mu X, where R naught is the count rate with no absorber present and mu depends upon the energy of the gamma ray photons. The graph below shows how ln of R varies with X for a particular source of gamma radiation. And then the graph below shows how the value of mu depends upon the gamma photon energy. Okay, this is a little bit involved. Okay, the table shows some sources and their associated photon energy. Okay, deduce which source was used for the investigation. Okay, so if we take the ln of the formula given to us, we will find that ln of R is ln of R naught minus mu X, so the gradient is mu. So minus mu is equal to, let's see, we can use any two values pretty much on this graph. So I'm going to use, let me see, 6.5, so okay, from 150 to 5, that's 540. Let me see, 540 minus 150, 390. Okay, so we'll use these 2 points. You can use any 2 points pretty much. I don't know why I'm hesitating about this. Okay, so 6 centimeters. So let's take this point, which is about there. So we will use this and that. Okay, so this is 390 and this is just 6. Okay, so mu is 380 I have in my notes for some reason, so let's use that. Let's work with that. 6.5. So mu is 60.31 centimeters to the minus 1. And if we use the graph that is given to us for 630, okay, so 60, okay, this is 10, 20, 30, 40, 50, 60. Okay, so 60 corresponds to an energy of 70 keVs. So for mu equal to 60.31 centimeters to the minus 1, the energy of the photon is 70 keV, which corresponds to xenon. So xenon 133 was used. Okay. I don't know, you can work out better, I mean, these values here in the graph and find a different mu that will closely match the 80 keVs of energy, but that's the idea, okay? You find the mu from the graph, and then you use the value of mu to find the photon energy, and then you compare from the table. Okay, and let's move to question 21. Okay. The first is a long writing problem. In the core of a main sequence star, nuclear fusion is converting hydrogen into helium. Explain the conditions required to bring about and maintain fusion in a main sequence star. Okay, so I'm gonna do this telegraphically. So high temperature in the core gives nucleons enough kinetic energy. Let's write it as key to save time. Enough kinetic energy to come close and fuse. Okay, kinetic energy. The kinetic energy must overcome the electrostatic repulsion. Okay, the density must be high, so that we get a high collision rate that maintains fusion. Okay, so pretty much in the core of the star, we need high temperature. Remember that high temperature means higher kinetic energy, right? And higher kinetic energy means that the nucleons can come together, fuse, and produce energy, okay? So we also need a high density, meaning that we need lots of nuclei, right? So that you have frequent collisions between them and higher probability for fusion. Okay, that's the answer. B. A helium nucleus is a particularly stable nucleus consisting of 2 protons and 2 neutrons. Calculate the binding energy per nucleon in joules of a helium nucleus. And we're given the mass of the proton and the neutron and the mass of the helium nucleus. Okay, first step is to find the binding energy itself. How do we do that? The binding energy is the mass excess over c squared. The mass excess is the difference in mass between the constituents of the nucleus, which for helium-4 it's 2 protons and 2 neutrons, minus the mass of the nucleus itself. So 2 mass of protons plus 2 mass of neutrons minus the mass of helium-4. Okay, this gives you 28.1 MeV over c squared. Okay, so the binding energy is delta M c squared, which is 28.1 MeVs because c squared cancels. And then we have to divide by 4, okay? So 28.1 over 4 MeVs gives us 7.025 MeVs. And if we convert to joules, because they ask to find the answer in joules, we find 1.12 times 10 to the negative 12 joules. And that's the binding energy per nucleon for helium-4. Okay, last question. The binding energy per nucleon of helium is relatively large. Explain why this makes the helium nucleus particularly stable. So it takes a lot of energy, actually 28.1 MeVs, or 7.025 MeVs per nucleon to break the nucleus apart. Thus it is stable. And that's it. I mean, is there anything else we need to say here? If we break, yeah, no, that's enough. That's good enough. So I'm gonna stop here. This was Unit 5 from, what was it again, January 2024. I'm happy to hear, some of you leave comments, and I'm happy to hear that you guys find some of these videos useful. I will try to upload more videos, and we'll see how it goes. So let me know what you think in the comments. Please like and subscribe and so on. See you in the next one.